Hello all, my name is Jonathan Yurch and I am a graduate student working with Dr. Josh Apty at the University of Texas at Austin. I am presenting on the spatio-temporal variations of PM2.5 in an urban environment using a network of low-cost sensors. This work is from a year-long study in the city of Bangalore, India. The problem that we are trying to solve is an issue of data availability. Air quality data in most developing countries is sparse, and many developing cities may only have a few sensors measuring air quality. These sensors cost tens of thousands of dollars, so it is often cost prohibitive to place more sensors in these areas. In the last 5 years, lower cost optical sensors have entered the public market. These sensors use optical properties of aerosols to estimate a concentration of ambient pollution. We brought 60 PurpleAir PAII monitors to Bangalore in the summer of 2019. These sensors measure 3 different size ranges of particles, but we focus on PM2.5. We started out by setting up all 60 of our sensors in co-location with a BAM 1022, a federally equivalent monitor for measuring PM2.5 as designated by the EPA. We performed an initial calibration of the PurpleAir sensors for 2 weeks in order to weed out poor performing sensors, set up an initial calibration curve, and determine the error between PurpleAir sensors. After this initial calibration period, we distributed 40 of the best performing sensors throughout the city. Our goal was to diversify our sensor placement based on land use. We also kept 2 sensors at the site with the BAM in order to develop a long-term calibration for our sensors. After the setup, we allowed all sensors to record ambient concentrations of PM2.5. We cleaned the data using 2 PM2.5 channels within each PurpleAir and removed all sensors that had less than 50% of valid measurements throughout the campaign. After cleaning and removing data, 31 sensors were used for analysis. These were classified into 6 broad categories, as seen in Figure 1. These sensors collected over 7,500 hours of data from August of 2019 to July of 2020. The following is analysis of the spatial and temporal trends that were revealed from these data. Figure 2 highlights a comparison between the median and 95th percentile of the year-long data set for all 31 sensors. As can be seen here, the median concentrations range between 25 and 37 micrograms per cubic meter, about 2 to 3 times the WHO level for healthy air. 95th percentile values range from 45 to 75 micrograms per cubic meter, which is 4 to 7 times the WHO levels. The sensors on the outskirts generally showed a lower concentration of both the median and the 95th percentile, indicating an urban influence of sensors in the urban core. The exception is the sensor on the far west, which is within 50 meters of a major road. Looking at the ratios in figures 2C and 2D, we compared both the interquartile range and the 95th percentile to the median. In 2C, it is seen that the interquartile range is between 0.4 and 0.8 times that of the median, showing that the interquartile range does not differ greatly compared to the median for all sensors, and the majority of the data are within 15 micrograms per cubic meter of the median. The ratio between the 95th percentile and the median show that the 95th percentile is about 1.8 times the median. This shows that a large majority of the data are within 2 times the median concentration, and even large concentration events are not dramatically large in Bangalore. In Figure 3, we zoom in on 3 sensors near the IISC Bangalore campus. One sensor was in the middle of campus, another was near the entrance of the campus by a major road, and another was in a nearby neighborhood. Comparing these 3 sensors that were within 2 kilometers of one another, the median concentrations were similar. However, as seen in 3B, the annual diurnal trend ranged greatly. Both the neighborhood and the near road sensors had diurnal concentrations that were similar. However, the inter-campus sensor had a much lower morning and evening peak, demonstrating the effect of green space shielding from different sources. This again is seen in figures 3C and 3D. Each of these figures shows the 10-minute average for October 1st of 2019 and March 1st of 2020, respectively. As can be seen, the near road and neighborhood sensors had far more peaks than did the inter-campus sensor. The near road sensor especially contained a lot of small peaks, which is indicative of nearby sources. However, the large peak in the evening for October 1st for the neighborhood sensor shows that there may be a large local source nearby this sensor as well. Similar concentrations occurred both in October 1st and March 1st for these three sensors in Figure 3. But as we move to Figure 4, we see an effect of seasonality on the hourly average data. In Figure 4, the data for each hour were averaged to create a diurnal trend for each sensor. The sensors were then divided by site classification. Two seasons, autumn and monsoon, were chosen to compare both the seasonality of particulate matter concentration and how each site classification differs between the others. Concentrations in autumn are shown in Figure 4a, and these are much larger than the concentrations in the monsoon, which is shown in Figure 4b. The morning and evening peaks flatten during the monsoon season. However, this is more pronounced in the lower concentration sensors, such as in the background sensors. This is most likely due to a lack of consistent local sources in the background sensors, as well as meteorological changes, though more work will need to be done to determine the magnitude of each of these effects. Looking at site classification, sensors near major roads had larger diurnal variability resulting from the influence of the nearby roads. Industry, high-density residents, and low-density residents all showed similar patterns, showing that outside of being near a road or background site, concentrations were generally similar. Finally, Figure 5 explores the ratio of each sensor to a background sensor. Every hourly point of each sensor was divided by the corresponding point of the background sensor, and the resulting box plot was plotted. On the y-axis, a value of 1 means that the hourly average concentration of one sensor is exactly equal to that background sensor. The box shows the spread between the 25th and 75th percentile, and the whiskers show the 5th and 95th percentiles. Based on our co-location study conducted in June of 2019, the normalized root mean squared error of all of the sensors was 5.4%, meaning that if the ratio was greater than about 5%, it could be assumed that the sensors are measuring differences between the background sites and other locations, rather than just the sensor error. In this figure, we see that the median ratio ranges between 1.05 and 1.5 times the background concentrations, indicating that there are differences between the different sites, measurable by these sensors. We also see similar results from Figure 4, in that the near-road sensors record much larger concentrations than the rest of the sensors, and all other sensors outside of these and the background sensors had similar concentrations to one another. So, through this study, we can conclude that low-cost sensors are a valid possibility for determining epidemiologically significant variances of PM2.5 in a moderately polluted urban area. Median concentrations in Bangalore over the year ranged by over 10 micrograms per cubic meter. Variance between sensors is greater than the error between sensors, showing that these sensors can discern the difference between background sensors and the rest of the urban area. We also see that temporal concentrations have larger variation than spatial concentrations in the city. Diurnal patterns are similar for similar site classifications and are reflective of diurnal patterns for ambient air. In the future, we hope to look at how much the urban environment contributes to ambient air pollution beyond the regional air pollution. In addition, we hope to explore how meteorological factors such as wind contribute to changes in space and time. Finally, Using the data that we collected, we hope to develop a model based on these data and apply it to the entire city of Bangalore. Thank you for all of your time in listening to this overview. If you have any questions, feel free to email me at jon.gingric@utexas.edu. Thank you to all of my co-authors who helped me on this project, and to the University of Texas at Austin President's Award for the funding for this project.